Good afternoon. Welcome to this afternoon's webinar. This is on Intelligent Transportation Systems, a part of the Traffic Academy. This is Victoria Beal with the Ohio LTAP Center. I'm going to go over a couple of housekeeping items and then I'll turn things over to our presenters for the day. The first housekeeping item I'd like to go over with you is that we have handouts for you available in the handout section of the GoToWebinar box. We have in there for you a copy of the slides for the complete presentation, and we'll update those at the end of the presentation series if there are any changes. We also have a reference packet for you. If you have any issues downloading those, please don't worry. I will send out links to them after the webinar today. I also have loaded in there 3 additional flyers for upcoming webinars you might be interested in. A restricted crossing U-turn that's going to be provided by Federal Highway. Also a self-evaluations and transitions plan webinar series that is going to be provided by Ron Eck, who's the director of the West Virginia LTAP Center for us. And then we have a webinar coming up on the TIMS system, which is actually a live demo of how to use TIMS. So if you have any questions on those or interested, they're in there. You can always reach out afterwards. The other thing I'd like to do is ask you if you would please look for the question box in the GoToWebinar panel, and please drop me a hi or hello in there. I ask you to do this because this is how we're going to be accepting questions throughout the webinar series, and I want to make certain that you know where the box is at. So looks like quite a few of you found it. That's great. I think that's all I have for now. So Charlie, are you ready?
Yes. All right. Well, thanks, Victoria.
Thank you.
I guess thanks to everybody for coming into the first standalone Traffic Academy course on ITS. Once again, my name is Charlie Fisher. I'm a statewide traffic operations engineer at ODOT. As you probably saw on the flyer, this is a new consultant pre-qualification certification for ITS design and operations. Come March 2021, all ITS design projects will require this pre-qualification. So glad you're here. We at ODOT, we're excited for this opportunity to share information that we hope will be helpful to your future designs. We have highlighted design and operational aspects that have helped us grow our ITS infrastructure in Ohio. There are a few of us from ODOT Traffic Operations on the line to chime in and answer your questions. Drew Janik, our lead designer, Alex Weinandy, who focuses primarily on signals and comms, but he's also our ramp meter expert. There have been considerable updates with ramp meters since the content was offered in the fall. Jamie Fink, who is our construction engineer, and Brian Comer, our statewide ITS engineer. With that, we're looking forward to this course, and we welcome your feedback as we go. We're fortunate to have Gannett Fleming's Kevin Hunt with us today to teach this course. Kevin is the regional manager of the Northeast and Mid-Atlantic Transportation Operations Practice with Gannett Fleming. He received his BS and MS in civil engineering, both from the University of Delaware. He has over 20 years of experience in planning, design, and construction of ITS and operations projects. Kevin's projects have spanned the East Coast from New Hampshire to North Carolina for the FHWA and internationally for Qatar. Kevin is a registered PE in 8 states and a certified professional traffic operations engineer. And with that, I'm going to turn it over to Kevin.
All right, well, thank you, Charlie. Welcome everyone to day 1 of our Traffic Academy webinar on ITS Intelligent Transportation Systems. As you kind of heard Charlie mention, this course was first included as day 3 to the Traffic Signal Academy this past fall. So you guys are some of the first to see this content. You know, we're currently scheduled for 4 1.5-hour sessions over the next 2 weeks, but depending on how things move, we may be able to finish this within 3 days. So Charlie gave a little introduction about myself. Typically I try and go around the room and get the feel for who's out there, but unfortunately with the amount of people on the webinar, we can't really do that. So I'll just give you a little bit of information. We had over 140 attendees registered for this course. It's a mix of DOTs, municipalities and counties, planning commissions, consultants, and contractors. The other thing I just want to point out here is acronyms. We've seen our first one here, ITS, or Intelligent Transportation Systems. There are a lot of acronyms that are used when we talk about ITS systems. So if I say one and you're not sure what it is, please ask a question, type it into that question panel, and we can address it. I'll try to keep them to a minimum, but sometimes I just go off on those. So Charlie mentioned some of ODOT's traffic operations staff that are going to be on today to answer some of the questions. Others out there are Jason Uray, who's the administrator and state traffic engineer, Brian Comer, who's the statewide ITS engineer, and Charlie, who introduced himself, the statewide ITS engineer. Drew Janik, after this course, will be your main point of contact for any questions that come up. You can see his contact information there. So many of you have likely taken the traffic signal portion course of the Traffic Academy. It will be some overlap, but I think it'll be a good reminder for those who may have been a while since you've had that course. So throughout this course, we're going to be covering various aspects that will allow you to develop a quality ITS plan. The course and passing the associated tests, as Charlie mentioned, is going to be a requirement for becoming pre-qualified in the ITS design and operations with ODOT. Additional information will be provided to you about the tests at the completion of the course. So what we're going to be covering throughout this, the next couple days, is going to be the references that will help you throughout the design process, the policies that guide the use of ITS in projects, the various systems and components that make up ITS, a discussion on the infrastructure, communication equipment, and mediums that are critical to an ITS system. We're going to provide some guidance on site selection for the devices, review the requirements for the design of ITS devices and the deployment of plans, and finally, some of the submission requirements. So getting right into references. All the references that we discussed today are available online. The top link is where you can find many of the commonly used ODOT reference materials. Under here, you'll find CAD standards, construction and engineering specifications. Let me bring this up real quick. So this is the website. In here, there's a whole ton of different references. You mentioned you got some of the CAD standards, the construction material specs. Coming down to the bottom, you'll find the traffic engineering manual, the supplemental specifications a little bit above it here that will be used throughout the design of these projects. Under the 2019 supplemental specs is section 809, which is for the ITS systems. So you'll see here, which we'll get into a little more discussion on in a bit. But you can see 809 is the ITS systems. So all this information is out there for you to use. These references are updated often, usually quarterly or biannually. So make sure you're checking them often because ITS does change quickly. The bottom website is ODOT's traffic operations website, where you can find additional information on ODOT's traffic operations program. You can see here on the side is some of the additional contacts that are out there. Some of the people that we've discussed today, like Brian in here and Charlie's on the second page. Down towards the bottom gives you more information on the different responsibilities on ITS, traffic signals, the ramp meters, which we've talked about briefly, are being recently revamped. Additional traffic operations standards, so you can find it on the Design Reference Resource Center list, but there's additional quick links here to some of the important reference materials that you need for these programs. So, as I mentioned, the ITS supplemental specifications are pretty robust and take precedence. However, there are several specifications within the construction and materials specifications that are applicable to ITS. The highway lighting item includes additional information on pole boxes, conduits, ground rods, wood service poles, and other associated items. And the traffic signs and signal specifications can also be used to help design associated ITS items, such as static signs, poles and supports, and cabinets. The associated specifications in the 700s will provide the material requirements and the technical specs for many of these same items. The main point you should take away from this is that ITS systems have needs from a variety of different areas, so you should always look at other sections to see if they can help. Now, the CMS here is updated quarterly. Now, the majority of ITS devices are located alongside the roadway, so you'll need to follow the clear zone requirements in Volume 1 of the L&D manual. Where possible, we want to try and locate the devices outside of the clear zone, but sometimes they need to be as close to the road as possible, or the location may not allow for meeting clear zone requirements. If the device cannot be located outside the clear zone, and even sometimes when it is, guardrail or barrier is required according to the protection requirements in the L&D manual. All lengths and need calculations will be required to be provided and make sure that everything meets the requirements. Volume 3 of the L&D manual includes the guidelines needed to prepare a plan set in the standard ODOT format. We'll cover more on this later, so I won't go into too much detail. However, we'll point out that ODOT does understand that some projects may involve unusual circumstances and that will require deviations from these guidelines. If you find that's the case, coordination here would be the key. And again, this manual is also updated quarterly. The next reference is the Traffic Engineering Manual, which I'm sure many people are familiar with, having likely gone through the traffic signal portion of this course. This manual is a consolidation of traffic engineering policies, guidelines, standards, and best practices. A lot of what we cover today is discussed in the TEM. The main relevant sections within the TEM are Part 1, which includes general information on the manual itself, standard construction drawings, design information and reference materials. Part 4, which includes information on traffic signals. And Part 13 is where the ITS information is located. Other parts that may include some information that could be used on an ITS project include the signs, markings, and temporary traffic control device sections. Now, this manual is updated twice a year, in January and July, unless there's a critical update which requires it to be updated sooner. You should always review Section 800 of the Supplemental Specifications to see what revisions have been made to the remaining specifications. The main specifications you'll need to pay attention to for ITS are Sections 804 and 904 and 809 and 909. These cover the majority of the ITS devices that will be deployed. You can see there are some other sections there that have pretty specific ITS applications, but for the most part, those other 4 sections will cover the majority of the devices. Now, Section 909 is not currently available, but it will be included in the July update to the supplemental specifications. So that should be out here in the next month or so. Sections 804 and 904 provide information on the fiber optic cable and its components, which we'll get into even more detail later on. These supplemental specifications are updated quarterly. Supplemental Specification 809 is the primary source for ITS specs and requirements. Amongst the other information, this includes requirements for closed circuit television cameras, dynamic message signs, ITS cabinets, ramp meters, and vehicle detectors. As I mentioned, the soon-to-be-released Supplemental Specification 909, that is based off the old Traffic Operations Handbook. So if you're familiar with that, a lot of that has moved over to this section of the supplemental specs now. It's going to include the technical specs for the ITS devices. These are going to be updated quarterly if needed. So for those of you who are familiar with the Traffic Operations Handbook, you should not be using it anymore in your projects come July when these are released. Now, there are also standard construction drawings. These details eliminate the need to create new details for each project. They're making it easier to include ITS in the projects by having these standards out there. Certain situations may require slight modifications from the standards, so if that's necessary, they should be modified and included in the plan set. Drawings include CCTV assemblies with both ground-mounted and pole-mounted cabinets, pole boxes and conduits, dynamic message signs, grounding, transformers, work pads and sloped areas, microwave sensors, and ramp meters. These drawings are updated twice a year also in January and July. Similar to the construction material specification, there are relevant drawings in other sections of the standard construction drawings. Particularly in the highway lighting and the traffic control sections, you can find a lot of supporting drawings that would be used in ITS projects. So as I mentioned before, take a look at other areas, make sure that they're not covered in other sections, some of these associated ITS devices. Now, there are also some plan insert sheets to take note of. These are not typically used unless there's a unique situation, but they can be found on the Resource Center list under the Traffic Standard Drawings. These may be phased out in the future, but for now they are still out there. The Traffic Authorized Products list is one of 3 locations where approved products can be found. For a device to be listed on the TAP, it needs to meet the 909 Supplemental Specifications, previously the handbook. There are processes for designers, contractors, and manufacturers to use the TAP. For designers, not all products on the TAP will meet the needs of an ITS project. So design engineers must confirm that the product is in the TAP meets their project needs. If it does not, the designer must follow the guidelines for obtaining approval of the proposed product. To get a new product on the TAP, there is a detailed product submittal and review process that a manufacturer would need to follow. This is updated quarterly. The 2 other locations for approved products are the Qualified Products list, which covers general construction items, and the Approved Products list, which covers specialty items. The links to these lists are shown here, but they can also be found on the Design Reference Resource Center. So those are all of the references we want to make you aware of. There's a lot of great information out there, so make sure you use it during the design process. All right, and we have our first question of the day.
And I have launched that. It says, which document contains products that meet all the technical specifications listed in the SS 909? And A is TAP, Traffic Authorized. B is QPL, Qualified Products List. C is APL, Approved Products List. And if you can't get your vote to record for some reason, it's probably because you have your screen in full screen mode. You just need to hit the escape button and then it'll let you record your response to the poll. We are not recording how you respond, so please just go ahead and choose an option there so we can get a good number of you voting and we can keep moving. Okay, we're getting up close to 70% voted, so I'm going to close the polling down now and share the responses. We have 49% that chose A, TAP, 29% that chose B, the QPL, and 22% that chose C, the APL. So I'm going to go ahead and hide that. And it's all yours again, Kevin.
Okay. Well, the answer is A, the traffic authorized product list. The QPL has the general construction items and the APL has the specialty items, but the TAP is where you'll find the products that meet the technical specifications that are listed in the Supplemental Spec 909. All right, and with that, that's the end of that section. Drew, did we have any questions come in that need to be answered?
No, nothing came in question-wise yet.
Okay. Sounds good. All right, moving on then. Next, we're going to look at the policies that guide ITS projects and the justifications for including ITS in a project. Now, this is important to note. The Federal Regulation 23 CFR 940 provides the process that a project is required to follow when federal funds are used. This is essentially referred to as systems engineering. The TEM provides further guidance on meeting the CFR 940 requirements in accordance with several sources. ODOT has developed a statewide ITS architecture, with MPOs developing regional ITS architectures that piggyback off the statewide ITS architecture. These architectures provide the framework to guide the planning and design of ITS, and they include service packages, interfaces, data flows, subsystems, and stakeholders, among other information. So if a project has aspects that are not included in the architecture, a systems engineering analysis is required. Preparing an SEA can help to control costs, reduce risk, maintain schedule, satisfy user needs, and meet the requirements of ODOT. The SEA should be commensurate with the size of the project. So if you have a small project, you may have a smaller SEA compared to some of the more complicated projects, big software projects, some things like that, that are going to require a more intensive SEA. Table 1397.1 provides examples of the three classifications of ITS projects. Exempt projects do not require SEA documentation. An example of this would be the expansion of an existing ITS system that does not change or add to the original needs and requirements of the system. So basically, this simply is adding equipment, adding a camera out there, adding a DMS to an existing system. Low-risk projects will utilize a system engineering review form, or SERF, to access or to assess the project, such as a ramp meter system or an adaptive traffic signal control system. High-risk projects will require a project-specific systems engineering analysis. This would be a project with new or unproven hardware or software. So what are some examples of ITS projects? The first one's on here, traffic signal systems are ITS projects. This could be a single traffic signal installation or more complex installations like an adaptive signal system. As you can see on here, basically any project that includes the acquisition of technologies or systems of technologies that provide one or more user services from the architecture is considered an ITS project. So in Ohio, a project would be considered an ITS project if it meets any of the following. It requires the integration of multiple separate systems, it's multi-jurisdictional technology integration, it replaces existing or installs new central control software, or it expands the freeway management system. If you're not sure, reach out to ODOT and they can help provide guidance. Next, we're going to look at some of the forms that are available to help you with this, going through the systems engineering process. The two of them up here are the minor ITS form and the systems engineering review form. But first, the application of the CFR 940 process is dependent on the funding source. I mentioned it before, the projects that utilize federal funds require the CFR process to be followed for the ITS-related items. So if you have a large highway expansion project that includes ITS, the process must be followed in accordance with that type of project that we discussed previously. Additionally, the products must be listed on the TAP. Otherwise, a system engineering analysis will be required. So if that item's not on the TAP, you need to perform possibly maybe a little one, but a systems engineering analysis will need to be completed. If an agency is using their own money, and it has to be 100% their own money, they are not subject to these requirements. The project does not need to follow the CFR 940 process, and they can develop their own specifications for items that are not listed on the TAP. This doesn't mean they cannot follow the process and they can't use items on the TAP. It's just that they're not required to. So the first form is the minor ITS form. There are actually two minor ITS forms. One for projects such as ROIS, road grip sensor systems, surveillance and control systems that can be functionally integrated into a freeway management system. And there's also a minor ITS form for emergency vehicle preemption. But that one can only be that, no other ITS components. Both of these forms include 12 items that need to be completed. The first is the scope of work, which includes the location, the description of the project, the ITS elements, and a project background providing a summary of the purpose and needs. Next is identification of the ITS architecture data flows that are to be implemented by the project. The form includes a diagram and a description of the flows. A list of agencies that are stakeholders in the project, along with their roles and responsibilities, is next. This will also include a brief concept of operations, including goals and objectives and operational processes. Identification of the functional requirements for the project is next. These define what the system must do. Then a description of the various technologies considered and why the proposed technology was selected, basically an alternatives analysis. The available procurement methods, such as low bid, design bid build, or P3, should be reviewed and analyzed. List of the ITS standards that will be implemented on the project, including federal and national standards. Testing procedures for the technology being deployed needs to be identified. And then a traceability matrix must be included. This is a vital document that is maintained throughout the project. It allows for traceability between the user needs, the system requirements, the design, the implementation, and the verification and validation. Next is documentation of changes that were made during project development and how they were accommodated, including changes in design, construction, and operations. Next is providing a maintenance plan and funding analysis for the maintenance and operations of the system after completion. And then finally, providing documentation for revisions to the regional RTS architecture to the MPO or the ODOT district. Now remember, this is the minor ITS form, not a full SEA. So these, although may sound daunting, these are going to be used for fairly established projects. So the level of effort here should be commensurate, as I've mentioned before, with the technology going in. So these are not going to be probably as robust as an SEA, which we'll talk about later. All right, the next document or the form is the SURF, which is used to determine if an ITS project can be considered low risk. Item 10 on here is the risk assessment guide. It's basically 8 yes or no questions about the project. If all the questions are answered yes, then the project can be considered low risk. So the SURF, along with a functional requirements document for the associated 7 project categories listed under item 4, will satisfy the SEA requirements. If any of the questions are answered no, then the project is going to be considered high risk, and a project-specific systems engineering analysis shall be performed in accordance with PEM Part 13. Any level of systems engineering work should not be developed in a vacuum, and input should be gathered from project stakeholders to help complete the forms and answer any questions about the project. Okay, proprietary items is next. These must be approved by the Office of Roadway Engineering. A request, including the model and/or manufacturer and the engineering justification that details why the item is necessary, shall be submitted to the Office of Roadway Engineering. They will coordinate with the FHWA and notify the agency of the decision. Now, we understand FHWA has lessened some of their proprietary approval requirements, but ODOT still has these in place and is still intending to follow the process that they have in the TEM. A proprietary request may be made if 50% or more of one brand is currently installed for that agency. Controllers, emergency preemption equipment, etc. could be examples of things that could be applied for proprietary approval. Now, if an agency is replacing all of their equipment, they cannot get proprietary approval. There are some additional conditions identified in the TEM for when proprietary materials can be applied for, such as no equally suitable alternative exists. It's essential for compatibility with existing highway facilities. So some of these are listed here and in the TEM. Now, there are other options to proprietary items as well, including approved equals, or you could request alternate bids, which we'll go over. So for approved equals, the big takeaway here is that all the products included as an approved equal needs to be listed on the tab. So any of these items that are not on the tab, project-specific SEA must be completed. So to do an approved equal, it must be on the tab. Again, local agencies can use their funds for items that are not listed on the tab. The other option was the alternate bid. This is the alternate bid procedure consists of adding a second bid item for each general item that is desired. So in these cases, the general bid item is sufficient to meet the project needs. However, the alternate bid item, in addition to meeting the project needs, also meets the agency's special requirements. So after opening the prices, the bids of both the generic and the alternate bid, they're compared. If the alternate bid price is higher than the generic price, the requesting agency will have the opportunity to reject the alternate bid or to accept them, with the agency paying for the difference between the generic bid and the alternate bid. So next, if an agency would like to purchase equipment separate from a construction project, a public interest finding may be pursued. For example, ODOT prefers to buy and install their own network equipment, so they'll prepare and submit a letter to FHWA for approval. And if they get that approval, they'll buy and install their own equipment. Now, this should be done early in the process, in the project, to reduce any potential plan changes if it is denied. All right, so that's the end of that section. We're going to have another poll question here.
I'm launching the poll question. True or false, CFR 940 is not required for a project using only local funds. And again, if you're having problems responding, hit the escape button to take yourself out of full screen mode. Looks like most of you are picking up on this really quickly though, so I'm glad of that. We are almost up over 70% already. Oh, there we go. Okay, I'm going to close the poll down and share the results. We have 89% that chose true and 11% that chose false. So I will hide that and I'll turn it back over to you, Kevin.
The answer here is true. The CFR process must be followed for projects with ITS funds that are related, that come from the federal funds. It is, followed for projects with ITS related items using federal funds, but not 100% local funds. So the answer there is true. So you got that right. All right, Drew, any questions on this section that came up?
Yes, we have one that says, who is typically in charge of filling out the forms that were sent over? So I'm assuming they mean for the SURF. I'm not sure.
Yeah, likely referring to the SURF and the minor form. These are going to be the responsibility of the designer to fill them out. However, as I mentioned, you should be coordinating with the stakeholders to gather input and feedback on the information that needs to be included. So, like I said, it shouldn't be done in a vacuum. You should be collaborating with all the stakeholders to make sure that you're meeting the system needs of the needs of the system. Okay.
That was the only one we
Any other
had.
questions?
Nope, that's it.
Have it now. Okay. All right, we will move on then. All right, next we'll discuss many of the systems and components that ODOT deploys, operates, and maintains. You can see a lot of them up here and their numbers, which are further broken down in this table. This shows you a list of the existing ODOT devices installed along the roadways in each of the districts. So as you can see from the table, closed circuit television cameras, dynamic message signs, and vehicle detectors are the most prevalent. This list is constantly changing. Just in the past year, nearly 130 ITS devices were deployed by ODOT. Many of these were CCTVs, but DMS and variable speed limit deployments are also increasing. And then a lot of the cameras that ODOT is deploying right now includes video analytics. So ODOT is able to operate and manage these devices around the state at the statewide traffic management center in Columbus. They can control the cameras, provide real-time traveler information messages to the DMS, travel time signs, variable speed limit signs, and to the queue warning systems. The TMC is staffed 24/7. Operators at the TMC monitor the urban areas of Akron, Cincinnati, Cleveland, Columbus, Dayton, and Toledo. In addition to providing real-time traveler information messages to the roadside devices, they also post information to the OGO website and mobile app. OGO features include live traffic camera images, information on freeway traffic incidents and work zone locations, travel delays, and DMS messages can even be seen on there. The operators also act as liaisons between the freeway service patrols and other public agencies that respond to incidents. The Freeway Service Patrol provides assistance to stranded motorists on Ohio's interstates. Some of the services that they can provide are helping to change flat tires, provide minimal amounts of fuel, and remove debris from the roadways. The operators also manage the statewide Towing and Recovery Incentive Payment Program. Through the TRIP program, ODOT pays pre-qualified heavy-duty towing and recovery companies incentives for the quick clearance of large commercial vehicles. Quick clearance not only reduces traffic congestion and improves mobility, but also improves the safety for motorists and incident responders. So you can see the TMC operators wear a lot of different hats and are critical to the operation of ODOT's roadways. As a whole, the ITS systems and programs deployed throughout Ohio have saved hundreds of millions of dollars and hours with a benefit cost ratio of 40-1. These savings will continue, although it could be via different devices in the future, because ITS, as we mentioned, is constantly evolving field. Now we'll discuss some of the various systems that are deployed, starting with closed circuit television cameras. So CCTV cameras are used to monitor the roadways and verify incidents. They can also be used to verify messages were posted properly to a DMS. ODOT records and stores video from the CCTV cameras for a 3-day period. After that 3-day period, the video is then overwritten. The CCTV mountings include pole-mounted, wall-mounted, and structure-mounted. For a pole-mounted CCTV, a concrete pole is the standard. It's typically 70 feet above the roadway. Some agencies do use steel poles, however, there's a lot more vibration, which can degrade video quality, especially when zoomed into an incident. So concrete poles are the preferred option in Ohio. In tunnels or other areas where a pole is not feasible, wall mounting is acceptable. And then finally, mounting the CCTV camera to a sign structure or other structure, typically in an urban area, can provide the optimal placement when a pole is not feasible. So those are your main mounting types. With the typical camera being mounted 70 feet above the roadway, including a lowering device on these poles is essential. Very few bucket trucks can reach the top of a 70-foot pole. The lowering device allows the camera and associated equipment to be lowered to the ground for maintenance. These devices utilize a crank, which accesses the cabling inside the pole via a handhole. The critical design aspect that should be considered is the location of the handhole. This handhole should be a minimum of 90 degrees from the arm of the lowering device, but preferably 180 degrees. We don't want a maintainer standing underneath the camera being dropped from 70 feet and something occurring which drops the camera quickly onto their head. You know, with the crank, the camera is typically lowered slowly, but accidents can happen. So for the safety of everyone, just make sure the access point is not directly under the camera. Another point to consider is the orientation of the lowering arm. Since the camera hangs below the pole, there is going to be some blockage from the pole when the camera pans around. The camera needs to be able to see the mainline roadway, merge points, ramps, and crossing signalized arterials. The pole should block, the image that's being blocked by the pole should be either a field or something that is not critical for traffic. And if you're unsure of what areas should be blocked, coordinate with ODOT and you guys can come up with an agreed upon solution. Now, ODOT installs various types of cameras. The first and most typical type of camera is a dome camera. These provide pan, tilt, and zoom capabilities, and they're suitable for most operations and have the various mounting types that we discussed. Next is a fisheye camera, which provides a wide-angle views of locations from one camera. They're typically used at signalized intersections and can provide views of all the approaches. Many of these types of cameras can give you a virtual pan tilt zoom to provide a more typical view of the approaches. Thermal and infrared cameras are mainly used to provide better images in low light and adverse weather condition situations. These can be used in tunnel applications and are also sometimes used for video analytics. Now, tunnel camera is used in tunnels and other situations where images may have a high probability of being occluded by spray from vehicles. You probably noticed the camera on the right includes a wiper for the camera lens. These are used where they need to be cleaned and often get, spray up on their lenses. Quad cameras provide 4 independent cameras that can look in varying directions. These are used at interchanges and signalized corridors for 360-degree coverage. Since the 4 video images are being sent to the TMC, these installations require a high bandwidth communication medium such as fiber or a leased line circuit. These cannot be utilized with the cell modem to send the video back. As I mentioned earlier, ODOT is deploying more CCTV cameras with analytics. The analytics can be used to analyze various situations and send an alert to the TMC. They can also provide vehicle counts and classifications. This type of camera is included on the TAP. All cameras installed need to be integrated into the central control software. For the CCTV cameras, ODOT uses the ITS Milestone Camera Management software and will lead the configuration of the cameras for integrating into the system. ODOT also requires the contractor to provide one complete CCTV unit, including the software, to test and ensure compatibility with the system. Additional testing requirements for the contractor are in Supplemental Specification 909.03, which will be out next month. That is the CCTV IP camera systems. All right, moving on to dynamic message signs. These are one of the most visible ITS devices. People driving around may not notice the cameras or vehicle detectors, but it's hard to miss one of these signs. DMS are key in providing information to travelers and allowing for informed decisions. They can provide travel times to destinations, information on incidents or congestion, and warnings about work zones. So it's important to note that ODOT does have proprietary approval for Daktronics. All the existing overhead DMS within Ohio are Daktronics. Now there are a few ground-mounted DMS for variable speed limits that are a different brand, but primarily Daktronics is used throughout Ohio. A full-size DMS is approximately 8 feet tall and 25 feet wide. These signs can be either monochrome, which is the amber you see on the left, or full color, which you see on the right. ODOT is transitioning more to the full color signs. So a monochrome sign has 27 pixels by 105 pixels. This also relates to a pixel pitch, which is the spacing from the center of the pixel to the center of the next pixel of 66 millimeters. The color DMS has 96 millimeters tall and 336 pixels wide. This relates to a 20 millimeter pixel spacing. So you can see the same size signs have different amounts of pixels. The color DMS has a lot more, which allows for a clearer text and the ability to display images. These are really the way that most agencies are going, is with the full color, more of like a high def kind of sign. For these types of signs, a walk-in enclosure is typically specified for maintenance aspects. So the DMS with a walk-in enclosure is typically the largest and most expensive signs. They're going to be mounted either to pedestal structures or overhead structures, truss type structures. These types of signs require ladders and catwalks for access, especially when they're mounted over the travel lanes. The enclosure allows maintainers to be protected from the elements and drivers when working on the signs. Protects the drivers by reducing equipment drops over live traffic. Non-walk-in signs provide access via either a front or rear access panels. These are typically used for smaller signs such as queue warning installations, and they do require approval from the Office of Traffic Operations for deployment. Because they do not have the enclosed work area, they may require additional MOT during maintenance. Typically, you cannot work on these over live traffic due to the potential for the falling debris. These types of DMS can be ground mounted in addition to overhead mounted. Queue warning signs are used near recurring congestion locations. Traditionally, the traffic was monitored by radar detectors, but ODOT is moving more towards the CCTV cameras with analytics for detecting the queues. Using the information from these devices, automated vehicle detection systems will identify slower speeds and potential queues, which are then relayed to travelers via the queue warning DMS. Queue warning DMS, as discussed, are typically front or rear access. Looking at the number of pixels, you can see that these are approximately 8 feet tall by 14 feet wide. Now, there are other ones for temporary portable DMS that can be used to provide queue warnings for special events or construction zones. So the DMS panel inserts are your smallest DMS. They are inserted in the extrude sign panels to provide a dynamic element. They provide a cost-effective strategy when the majority of the information is static and are being used to provide information on travel times or truck parking availability. The inserts are typically about 2 feet by 4 feet, but can be modified to meet the need of the information. These signs are also typically Daktronics. There are some older versions out there from another manufacturer that, as they break, are being replaced with Daktronic signs. Similar signs are the destination dynamic message signs. They provide information on travel times to set locations. Typically, these are deployed when leaving urban centers. The information they provide help travelers make informed decisions on route choice. Travel times are calculated via an algorithm that uses data from third-party providers. As you saw on the amount of devices that were installed within the last year, one of the newer DMS applications that's being deployed by ODOT are variable speed limit signs. These signs can be very beneficial to lower the speed limits in areas that experience sudden weather changes or recurring congestions. They're typically an insert also on a regulatory speed limit flat sheet sign. Currently, VSLs are only approved for sections of I-90 and I-670 where they've been deployed. And they can also be deployed on I-275. So if you have a project that VSLs are being discussed, you're going to need to have discussions with ODOT on how those regulations can occur. Now, work zone VSL signs are different, all under separate regulations. So if you have VSLs in a work zone, those can be deployed on other routes. Right, managed lanes are another ITS applications that is used to increase the capacity of an existing roadway facility. These are unique designs, and the Office of Traffic Operations will work closely with designers and provide guidance as necessary for these systems. This is another one where you're going to need special approval to deploy these types of systems. Regardless, DMS are critical to the success of these projects. Travelers need to know the availability of lanes, if there's congestion ahead or incidents. And as you can see in this image, the X over the left shoulder is indicating that the shoulder is closed to traffic. So ODOT's first managed lane project was the Smart Lane on I-670 in Columbus. This project allowed for part-time travel on the inside shoulder. The photo on the previous page was an image of one of the actual DMS in operations. Gantries were spaced approximately 3/4 of a mile apart, and it's over all the travel lanes and the inside shoulder, the DMS is. Once traffic congestion hits a certain level, the speed limits will be lowered and the shoulder will be open to traffic as indicated by a green arrow. Any additional information that needs to be provided to the travelers will be posted to the center of the Smart Lane DMS. For this project, there was also an emphasis on camera coverage. If there's debris or a broken down vehicle on the shoulder, the Smart Lane should not be open to traffic. So in addition to the 70-foot PTZ camera poles that were providing full coverage of the roadway, 3 analytic cameras were installed on the structure to monitor the Smart Lane. Two of these analytic cameras were static cameras that pointed in either direction, and the third camera was a PTZ camera, all out over the shoulder. Now, there are some other specialized DMS that may be considered on a project-by-project basis. These types of installations should be coordinated with ODOT. You can see some up here is just an independent lane use signs or road closure notifications. Ramp meters are used to control the frequency that vehicles enter the freeway. The goal is to prevent the breakdown of traffic flow and improve the operation of the freeway. ODOT has recently developed new standards associated with overhead mast arm ramp metering installations instead of the pedestal mount design that you can see in the left photo. The installation detail can be found in the standard construction drawings under ITS 76.10. So some of the benefits that are realized from a ramp meter being installed include the reductions in travel times, crashes, and vehicle emissions, while increasing vehicle speeds on the main line. ODOT maintains 38 ramp meters statewide currently. Another recent update was the development of guidelines for a ramp meter warrant analysis. These new guidelines can be found in section 1303-11 of the TEM. A warrant analysis must be completed before the installation or design of a ramp meter. There are two types of warrant analyses. One for determining if an existing ramp can be retrofitted with a ramp meter, and the second for determining if a future ramp meter is needed on a project and design. The flow chart shown on this slide is for the retrofit analysis. There is a separate flow chart for a future analysis. There are 9 total warrants, including both ramp meter and mainline volumes, crashes, mainline speed, and freeway level of service. Warrants 8, which is acceleration length, and 9, which is the ramp storage length, are not analyzed as part of the future ramp meter, as it's assumed the proper lengths can be designed into the project, and they're used to verify that those lengths are appropriate. Another aspect of the future ramp meter analysis is the potential for a phase spillout. So the warrant analysis will be completed with traffic data that is projected both 5 years out from the design date and 10 years out from the design date. These will be utilized to determine when the ramp meter meets the warrants to be installed. Depending on when it is warranted, will determine what components get installed as part of the project. This will ensure that a ramp meter is not installed and sitting idle if it's not needed for several years. So if a ramp meter is warranted within 5 years, a full build-out will be included with the project. If the ramp meter is determined to be warranted between 5 and 10 years from the design date, the project will include a majority of the equipment, but it won't include the signal heads, the signs, the wiring, or the cabinet. If the ramp meter is not warranted within 10 years, nothing will be installed. So in addition to the wear and tear on the equipment when it's not needed, this will also ensure that the technology being deployed is the most recent. Ohio's revised code states that a dark traffic signal indication is a stop condition. Therefore, when a ramp meter is installed, it must rest in green when not actively being used. Another reason why the signal heads will not be installed too early. The operation is planned for 1 vehicle per green, with the metering rate set to ideally not exceed 15 vehicles per minute. This will help to prevent vehicles from rolling through the signal without stopping. The ramp meters will operate in either a traffic responsive mode or a time of day mode, depending on conditions. If volumes are pretty consistent, a time of day mode may work best versus a main line with large fluctuations in traffic, which would likely warrant more of a traffic responsive operation. Wrong-way detection systems are deployed on ramps that meet certain criteria. The system is comprised of vehicle detection, a DMS to notify drivers they are going the wrong way, and are tied into communication systems for notification to the TMC. Approval for installing a wrong-way detection system needs to go through the Office of Safety. Additional information is included in Supplemental Specification 809.18. Now, detection for these systems is one of the main components. They can either be radar detection, which requires a dual system for confirmation, or a CCTV camera with video analytics. 809.18 includes the additional information on the wrong-way detection system and all their components. Truck parking systems are deployed around the state through a design, build, operate, and maintain contract. There are 28 locations with the truck parking signs for about a dozen rest areas that provide parking availability information. So if a truck driver was planning to skip the next rest area and park at the following one, but sees that it's nearly full, he may change his decision and stop at the closer one. Hopefully this is eliminating a dangerous situation of the trucks parking on the shoulder and identifying where there's available parking. There are no future expansions of this system planned at this time. A road weather information system collects information on weather conditions at important locations. These systems have various sensors that collect data on temperature, visibility, wind, precipitation, roadway and subsurface temperatures, and in some locations, flood information. This data is used to develop forecasts and disseminate road weather information to help maintenance staff make decisions, including when and where to deploy snowplows and warranting the application of salt and brine to the roadways. The information is also used to disseminate information via the OGO website to travelers in order to influence their decisions. For support on these types of installations, contact the Central Office of Traffic Management. So connected vehicles, which I'm sure everyone knows a lot about, but this is essentially the use of technologies for vehicle-to-vehicle, vehicle-to-infrastructure, and really vehicle-to-anything communications. The CV infrastructure term is applicable to both roadside units and onboard units. In Ohio, Drive Ohio handles all CV applications. So if you're working on any projects that incorporate CV technologies, notify Drive Ohio and coordinate with them. Roadside units are deployed, as you guessed it, on the road. There are many factors that need to be taken into consideration when deploying these units, such as FCC licensing to ensure the bandwidth is available with no interference. Most deployed RSUs to date are utilizing DSRC technology. However, cellular vehicle-to-X communications is a rapidly developing format. There's a lot of manufacturers right now that are developing dual RSUs that are capable of both DSRC and CV2X communications. However, these cannot be used at the same time for the communications. Both technologies utilize the 5.9 gigahertz band for communications, and the FCC is currently considering opening the lower portion of this band to unlicensed devices, thus cutting the availability of bandwidth for the CV applications. This decision is still not finalized, so once it is, it'll probably have a major impact on the communication technology that's going to be used in the future for connected vehicles. Again, coordinate with Drive Ohio if you have any of these types of devices on your projects. The other piece is the onboard unit, which goes in the vehicle. This will have a human interface device to provide information from the roadside unit. Right now, signal phasing and timing and basic safety messages are the main information being provided, but these applications are being expanded every day. Finally, we'll briefly discuss a technology that is being phased out by ODOT, Highway Advisory Radio. With many of the new ITS devices, this technology is becoming obsolete. So as parts fail on the existing equipment or a sign gets hit, the locations are being eliminated. And now we have time for another question.
Okay, let me get this poll question launched. And while I'm launching the question, I do want to mention that we will be emailing out the handouts as far as the slide presentation and the reference packet after the webinar concludes. So if you, for some reason, missed something that was being covered, you'll be able to see that information in the packet. So where in what section of the TEM, section 13, can you find the ramp metering warrant? And A, we have section 1301, B is 1302, C is 1303, and D is 1325. And we've got about half of everybody voting right now. So we'd like to get that up over 70%. So if you don't know for sure, just take a guess. But, you know, just remember that there will be a test that everybody has to pass after they've completed these in order to get your name on the pre-qual list. So if you don't get this answer right, you might want to mark it down and make it one of the things you go back and review. Okay, we've got quite a few people who voted now. I'm going to close that up and share the results. We have 6% that chose 1301, 7% that chose 1302, 72% that chose 1303, and 15% that chose 1325. So I'm going to hide that, and it's back to you, Kevin.
Okay. Well, the majority got it right. It is answer C, TEM section 1303-11 gives a breakdown of retrofitting an existing ramp, or if a ramp is being designed with future characteristics, volumes for less than 5 years, 5 to 10 years, or more than 10 years out. So good job, everyone. All right. Drew, do we have any questions on this section?
Sure, yeah. There was a couple that we actually sent answers out to while you were speaking, but there was one that I wanted to expand on a little bit here. It said, how did the percentages of smart lane activation since COVID-19 compared to pre-COVID conditions? So the Traffic Management Center has not turned on the smart lanes since Friday, March 13th for congestion or peak hour travel. They have closed lanes as needed for construction. Pre-COVID, it was basically Monday through Friday around 3:30ish until the rush hour subsided. So hope that gives a little bit more information. But other than that, there are no questions.
Okay, great. That's interesting information to have too, you can track. All right, I think we have time to get through the next section as well. So we'll move on to communication networks. So this is the next important part of an ITS system. A lot of data is sent between the TMC and the devices in the field. So two important concepts to take into account when identifying the appropriate communication medium are bandwidth and latency. Bandwidth is the rate of data that can be transferred across the communication medium. For example, megabits per second or gigabits per second, whereas latency refers to the time it takes data to move from point to point on a network. It's also known as delay. So typically these are measured in milliseconds between devices. So those are the two main concepts that help drive how the communication mediums are used. Next, there are several communication mediums that are available for the network. The type to utilize will be determined during the scoping process. Fiber is always preferred. However, funding constraints can limit its use. ODOT has an extensive fiber network in both the Columbus and the Cincinnati areas, and also a little bit in Toledo, and Akron. Lease lines are another one that's used extensively throughout the state. And you can see some of the other ones being cellular and wireless, probably the next two prominent mediums, and copper, which is pretty outdated at this point. So Supplemental Specification 904 is where you will find the technical requirements for the fiber optic cable and their associated components. You can see all the different components here in this list. Single mode fiber optic cable is used for backbone or trunk installations. Backbones are a fiber run along a roadway. They typically come color-coded buffer tubes of 12 fibers each, which are then also color-coded. The number of buffer tubes will determine the number of fibers. Typically, the backbones will be a higher fiber count, like 96 or 144. Multi-mode is the other type. It's not used too often, so you want to make sure that you are getting single mode fiber. There are several other methods for installing fiber optic cable. Pulling is the most common. However, ODOT is beginning to use air-blown fiber more often. Microduct pathways and multiple microducts, or are multiple microducts within a single jacketed duct. 7 microduct pathways are the most frequently used, but 4, 2, and 1 microduct can also be used. So the fiber optic interconnect cable is not used too often by ODOT. Basically, it converts a 250 micron fiber, which is the diameter of the fiber, to a 900 micron fiber that can accept standard connectors for connection to a termination panel. A drop cable is a smaller fiber count cable, usually 12 or 24 is typical, that will be spliced or connected into the backbone cable in a splice enclosure and run to the cabinet. Drop cables have to meet the same requirements as the single mode fiber optic cable being used on the backbone. Patch cords, which is the next one, are single fibers equipped with connectors at each end. So these are used to make connections between 2 fiber components, such as a switch. The termination panel is installed within an ITS cabinet and is another device that the drop cable is connected to. The drop cable fibers will be terminated on this panel. Then, depending on what each fiber is designed for, the appropriate connections are made for this device. Sometimes they might connect to another fiber in the backbone, sometimes they'll connect to a switch. So this is all done on the fiber diagrams that will be talked about later. So with the termination panel SS, there are requirements for an MPT cassette. The MPT cassette splits out the MPT to separate LC connectors. Now, the ends of the fibers typically have connections. There are several different types of connections that go on the ends of the fiber. ODOT primarily uses LC type connectors. Next is a splice enclosure, which is used to make all splices between the fiber. The size of the splice enclosure will be dependent on the number of fibers that need to be spliced together. They must be waterproof, rodent-proof, re-enterable, crush-resistant, and are installed within pull boxes. Fiber optic media converters are being phased out. They're being replaced by switches, which provide more functionality. So this is more of an older technology that's not used as often. A transceiver sends and receives data. It converts electrical and optical signals for transmission over the fiber optic cable. Many use two fibers, one to transmit and one to receive. Some will use one fiber to both transmit and receive, but they can only do it one at a time. You need to make sure in your designs that between two devices, the transmit is connected to the receive on the other end. Otherwise, your communications will not go through. The range for sending information using a single mode transceiver can be as high as 100 miles. So these can go pretty far. But there are also limiters on the bandwidth of the system. When designing a fiber network, a redundant ring is desired, but not always possible. A redundant ring will allow for communications in both directions. Therefore, if there is a break in the fiber, the communication to the device will go in the other direction. Ideally, the redundant ring is created via separate fiber routes, i.e. fiber on either side of the road or on different roads that all connect together. But sometimes a collapsed redundant ring will be designed. This is all being done on the same fiber backbone. If you have a single run of fiber along a corridor at the ends, they can be looped back on each other to create that collapsed ring. A router is a network device that uses IP-based addresses to transport data between devices and networks. If these are deployed in the field, they are not designed for hot or cold temperatures, and they're not designed for hot and cold temperatures. Additional environmental features such as heaters and fans may be required in the cabinets. Network switches are similar to routers, but the devices they send data between have to be on the network the switch is assigned to. ODOT uses proprietary Cisco switches. Ideally, IT policy states that managed switches should be used. There are two types of switches, unmanaged and managed. An unmanaged switch allows for Ethernet devices to communicate between each other, but that's about it. They have a fixed configuration. They're basically plug and play. A managed switch provides the ability to configure, manage, and monitor your local area network. It provides greater control over how the data travels over the network, also allows for monitoring of the devices on the network, and sometimes troubleshoots the switch without having to go to the field. So managed switches are more expensive, but they're still desired. Wireless is another medium that can be used. A lot of those devices we just talked about were associated with fiber backbones, but line of sight is required between the antennas. There are several bands on a radio spectrum that are designed for use in these applications. The 2.4 gigahertz and the 4.9 gigahertz are not typically used by ODOT. As I mentioned, the 4.9 is starting to be used a little more by connected vehicles. But wireless is typically only used for last mile or point-to-point applications. So as I mentioned, fiber is desirable, but wireless is an option. Cellular modems are solutions where other communication means are difficult or expensive to install. ODOT uses Sierra Wireless for their cellular modems. Like your cell phones, these can connect to the 3G or 4G and soon to be 5G network, although 3G is being phased out by Verizon, so it's more now the 4G and 5G as an emerging cellular technology. You can see the estimated speeds in comparison to 4G, but this is the reason the 5G is being touted for future roadway technologies. I mentioned IP addressing in many of the components. Traffic operations will assign the IP addresses, configure the devices, and typically will install the communication devices in the field. They need to know what is going in. The IT network and security team will manage the security of the system and firewalls. These firewalls are needed to prevent people from hacking into the system. So as I mentioned, Columbus and Cincinnati have pretty extensive fiber networks. Throughout the rest of the state, various mediums are being used and deployed, such as the cellular, the lease lines, and the wireless. All right, and we have another poll question.
Great. Now, on this poll question, I'm going to launch it, but I'm going to read the full question off because I couldn't get all of the text to fit in there. So the full question is, which interconnect type is described as a radio type bridge between two devices with clear sight lines no more than 3 miles apart to communicate? And then you have your options there on the screen of A, fiber optic, B, wireless, C, cellular, and D, leased line. So everybody's voting very quickly. So that's great. We appreciate that. We only have about 9 minutes left in the session today. So, all right, I'm going to close the poll up and I will share the responses here. We have 3% that chose fiber optic, 87% that chose wireless, 8% that chose cellular, and 3% that chose lease line. I'll hide those and it's all yours again, Kevin.
All right, the answer here is B, wireless. Fiber is the preferred communication medium, but it's not always feasible based on the site or the cost. So these options can give you more flexibility to get communications to an ITS device. All right, Drew, any final questions that have come in on this section or throughout the entire day?
Yeah, we answered again. We just would kind of answer them in the background and send them back out to people. But their last one just came in here. It says, besides ramp meter warrants, are there any warrants for other ITS devices that are used? And right now, I believe it's just the ramp meter. We don't have any other warrants right now for ITS devices.
Yep, I believe that's the case, other than traffic signals, but
correct.
That's another type of ITS device. So, okay. Well, as Victoria mentioned, we only have about 9 minutes left here, so I think this is probably a good stopping point for today. Any other final comments from Drew, Victoria, Charlie? Anyone?
On my part, I just want to mention that we do have the questions collected, so it'll be up to Kevin and Charlie and Drew, but they might possibly put those in a format where they can share them out with everybody as far as the questions and the answers that have been provided along with that throughout the webinar time today. And the way we did this series of webinars is you registered once for all of the webinars. So you'll be using the same link again to join us for the next session. So we will look forward to having you on that session. But in the meantime, hopefully the recording has worked and I'll get that posted and a link emailed out to you along with links to the slides from today and also the slides, or excuse me, the handout with the reference materials. So as far as the next session, I'll send that information out to you just in case you need it. And yes, a reminder should be sent out like it was today. But again, I'll make sure I get that information out to everybody as a reminder about when the next session is. So thank you everyone for being on here. Are there any final questions from Drew and Charlie?
No, I think I'm good.
All right. Well, thank you everyone. We appreciate your time and we look forward to seeing you on the next one.
Thank you for joining us.